we go. I think I'm doing everything right. Nah, I don't know. I don't know anymore. How does this technology work? All right. Apparently, theoretically, we are live. In theory.
See us.
Yeah. So, been playing around with the Starlink some more. I told you I got that. I don't know if you...
I didn't know you got one.
Yeah, I got one. Yeah.
How is it?
It's pretty amazing. Yeah. Like, it makes complete destruction of the night sky just almost worth it.
What does it cost?
It costs $750 for the box, for the dish, and then $130 for the service every month. Canadian, yeah, which is $5 US.
I think it's $100 US in the beta.
Yeah, I think so. Yeah, and I
a
pay
little piece of your soul.
And I pay $120 a month for my existing internet service. So this one's not. It's not like, for where I live right now, Starlink probably won't work in its current configuration for the long term, because it's having trouble. Like, it's missing about maybe 10% of its time accessing, blocked by the house, by fences, by neighbors, by trees. So I'm gonna play around with it and like move it around my yard and find out if there's a place, and maybe even like put it on the roof and see if there's like a place I can put it where it's mostly getting access to the internet, and then have a satellite installer come and actually lock it down there. But I'm assuming over time, if they're going to develop an algorithm so it figures out which parts of your property are blocked, and then also, as there are more satellites, it can spend more time focusing on satellites that it can see and less on the ones that it can't see. But the download speed is fast. Like, it's absolutely as good as broadband. 150 megabit down. Upload speeds are good, 50 megabits up. And I'm seeing ping times down as low as 18, which you can play an online video game at that. So
I don't even think I have 50 megabit up on my fiber internet.
Yeah, it's early days though, right? I mean, they're limiting the number of people who are able to go into each cell. So so I'm assuming over time the speed, as the speed will go down, and then the more satellites will come online, and the speed will go up, and it'll be a bandwidth issue. I think there's like 2 gigabits of bandwidth per cell. Maybe there's more than that. 50? Anyway, there's some limiting amount that they're able to provide. But yeah, and so I mean, I think, like, before Starlink came out, I mean, I've gotten into a couple of arguments with people on the internet about this, and they're like, ruining our sky for what benefit? And I mean, $130, that is accessible to regular Canadians. Right.
It's a good first world price.
Right. It falls short of giving it to the next billion people.
That absolutely, by no means. But when you think about things like, you've got Aboriginal communities in Canada, which are, we have tons and tons of these really small communities, 50 people, 100 people, and they're disconnected by 100 kilometers to the nearest town. So they've just never been able to get internet of anything beyond dial-up, and so now suddenly they're able to get really good internet. So it's I mean, I'm torn. If it was $10,000, I would say it's an awful cash grab and it's terrible. Like Iridium. Like, Iridium is not for regular people. Iridium is for super rich people who live on their super yachts and they want to call from the top of Mount Everest. But at this price, Starlink is accessible to middle-class people. Definitely not accessible to the rest of the world yet. But then I can imagine them deploying things like a Starlink, you put up a receiver in a town, and then you just turn it into, you've got a nice mesh network. Suddenly you're supplying.
Get nice wideband Wi-Fi out there, and like in a plane or something, you could cover a long distance.
Yeah. If you've got a town, I mean, you got that 50 people, you could provide Wi-Fi to the entire town for $100 a month, which is, so that's kind of reasonable. So, And then it's, in theory, prices will only go down as competition comes up. So I think my worst fear that this would just be a way for banks and rich traders and people on their super yachts to make more money is being, that has not come true. So we still are losing chunks of our night sky. And I mean, the astronomers are sad, but the internet's, but it's, again, I mean, I do sort of, I want to make a video. I think I want to like explore this idea just from both sides and just like start, just like not give any answer, just like go like, here's what we're losing with the night sky. And here's what people in remote communities who have been cut off from the modern internet are gaining. You decide, because it's not my, I can't decide. I'm going to say hi to a bunch of people, which I always forget to do. Hello to Andrew Planet, Astro B, Ben Kalo, Corey S, David Dunn, David Fairweather, Horizon Brave, John Musk, Johnny J, Larry King, Nancy Graziano, R. Joan, Roger Haskins, Ronald McCoy, Sergusi. Whoa, just changed. All right. Susan Hunter, Zach Perry. And there's a bunch of people who said hello, but I guess they timed out. Anyway. All right, we've hit the 5-minute mark, so I guess it's time to start. I'll put you all back in your boxes. And focus on me. What about me? Okay. And here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, January 20th. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about calculating the digital color codes of stars. NASA gives up on InSight. What happened with the SLS Green Run, and a whole bunch of alternative propulsion systems are being tested with Cubesats. Joining me this week on my screen right now, I've got Morgan Rembert. Hey, Morgan.
Hey, Fraser. Happy New Year.
Happy New Year. A
lot of good space stuff in the new year so far.
Have we not hung out in the since before the new year?
I don't think so.
No.
It's a brand new world.
Yeah, in the olden days, it was a lot more simpler for me to remember when and how I'd interacted with the various co-hosts of the Weekly Space Hangout. But now, with
we're drifting apart.
Yeah, well, just rotating hosts. I just I don't remember, and so I just assume this is the first time we've ever met.
It's nice to meet you.
Nice to meet you too. All right, and we've also got Alan Russell. Hey, Alan.
Hey, nice to be there correctly this time.
Yes, yeah.
I tried to connect yesterday because it's Thursday morning here, and I got confused by the dates. So
yeah. I woke up this morning and had a message in my email that Alan had joined my Zoom meeting, and I'm like, why? What? And then I sort of later on today I was like, oh, he thought today was yesterday. Okay. Yeah.
So the brightest minds on the show, yeah.
Yeah. So you got up at 2 a.m. twice in a row.
Yeah.
That is really impressive. I'm
so tired.
Yeah. So tired. I do admire the I guess the seriousness of you and Nika who are showing up at like 2 a.m. for your time. That is really, doing a science. All right. Before we get on to this week's guest, I want to give, of course, a gigantic shout out to our good friends at the Weekly Space Hangout crew. Now a message from our sponsor, the Weekly Space Hangout crew. They are, of course, the executive producers of the show. They are our friends, our fans. They're the ones who organize the guests that we're going to have. They really decide the format of the show, help sort of choose who the co-hosts are going to be. Every day that goes by, we lose more control over this show and just become really just puppets to our good friends at the Weekly Space Hangout crew. So if you want, and I'm not kidding, if you want ultimate cosmic power in the space science journalism community, you should join the Weekly Space Hangout crew. Go to wshcrew.space. They'll give you all your marching orders, credentials, executive producerhood, and you can go out and bring on guests to this show. Speaking of guests to this show, I would like to join two people welcome to Dr. Aaron Rosengren and Di Wu.
Hello. Hello. Happy to be here.
Thanks for coming. And I feel like this is one of the few times that we've actually had two people show up on the screen at the same time. And normally it's really tricky to do an interview with two people when they're in separate regions, and I sort of go a little crazy. But to have the two of you in the same room, this is perfect. I love it. So who are you? What do you do?
Yes, I'm a faculty member in the Aerospace Mechanical Engineering Department at the University of California in San Diego, and Di Wu is a Ph.D. student in the same department. So.
Yeah, I work for him.
and so, what brings you to the Weekly Space Hangout?
Yeah, so we have a collaborator in Serbia. It's Nataša Todorović, and it was really a long process that we've been working on this topic of space manifold dynamics, which is kind of sounds esoteric. But it's really been used a lot in modern space mission design, we sort of tailored that type of knowledge to the region around Jupiter, and really found this really interesting result. So.
Now this idea of, what did you call it? Space
manifold dynamics is sort of the catch-all now.
That's really cool. But the gist of that is that you're essentially using the various interacting gravity wells of the solar system go from world to world with minimal amounts of propellant. I sort of think about like things like the Lagrange points, right? So you're able to kind of go, there are these like gateways to go from one part of the solar system to another part.
Yeah, pretty much. But that's like the traditional point of view of manifold, but also manifold could be fast. It's not only just limited field, but it could also like limit your time.
That's interesting, because I did a video a couple of years ago about this idea of the interplanetary superhighway, I think it was called, and that there was essentially a very low fuel way that you could go from pretty much anywhere you wanted to go in the solar system. The only problem was that you had to pay an enormous amount of time, like hundreds of years, if you wanted to get from, say, Mars to Jupiter. But I understand you found some faster ways.
Yeah, so the interplanetary highway network is sort of like the foundations of this whole field, and it's been understood for probably about 2 decades now. Our colleague Shane Ross did a lot of this work back when he was doing his Ph.D. at Caltech, actually, and those are sort of like the slow back lanes of the solar system. So we found some like pretty fast highways. We're still looking at the implications of them for spacecraft travel, but it turns out that they actually guide a lot of the motions of these small bodies in the solar system between Jupiter and Neptune, called centaurs, and of course Jupiter family comets, which centaurs eventually become.
So how fast?
Well, it really depends, I guess, what conditions you have, orbital configurations you get, but we found trajectories that, because of these sort of close encounter, that the manifolds bring you really close to the planet. And of course, we know about gravity assist from Voyager and New Horizons. All these missions take advantage of gravity assist in particular, but they sort of do that in a way that they just go as fast as they can to get to Jupiter, and then they let Jupiter kick them a little bit further by taking that energy. You can actually go into different regions that'll take you there naturally, and those will throw you out due to the same sort of instabilities. But we found some trajectories that get you from Jupiter to Neptune, and I guess
like 10 years.
That's crazy.
Yeah.
Wow. So it's kind of like a natural gravity assist that's taking you from the orbit, the region of Jupiter, some flyby that then kicks you out all the way out to Neptune in about 10 years, which is kind of the speed you would go if you were flying from Jupiter to Neptune. I mean, maybe you go a little faster, but that's kind of impressive.
Yeah, it depends on really the hyperbolic nature of the resulting trajectory that you get on when you actually put yourself on one of these manifolds, and so there's a whole totality of solutions. Some results actually can cause you to crash into Jupiter.
Right, those are bad ones. Yeah, okay.
Those are the bad ones for spacecraft, but maybe for protecting our planet from near-Earth asteroids, those are the good ones, right? So,
right. Yeah.
Like you can think of a Schumacher-Levy 9 that collided with Jupiter. That was actually brought in. There was a recent paper by Martin Lowe and one of his students that showed that actually follows the path of a manifold into Jupiter. So that's actually what controls sort of the fate. You could think of these as kind of like conduits in space or space pathways that are crafted by the gravity of the different interacting, planets. And in what you said with the Lagrange points, those are sort of seminal to the understanding. But yes, these are very interesting different totality of solutions in states that you can get with this type of dynamics.
I mean, I always describe, like, when people imagine the solar system, they sort of imagine the sun at the center of this disk, and then all of the planets are farther out on this disk. And sort of our intuition says, oh, there's like force that's kind of pushing you outward in the solar system. But a better way to imagine is that it's a mountain that you're climbing with the sun at the center and the planets sort of higher and higher up this, the mountain range to the amount of energy that's required to get you higher and higher and farther away from the sun. And yet with these planets, it's if they're able to drag you up this mountain with their gravity, and suddenly there's like a free travel all the way up and out of the solar system. Could you actually get out of the solar system in the end?
Well, if you're on a hyperbolic orbit, eventually you're unbounded to the sun, so eventually you will escape. But the furthest I think we've seen some of these bodies get ejected to was what, about 300 AUs or something, all the way to the scattered disk. So there's a lot of different end states. Also, some objects can get reduced in their energy, and they can actually become near-Earth asteroids. So there's a different side of the coin here, and different implications that come from this. So, I mean,
the solar system's had a long time to get up to a lot of mischief in working with all of these different orbits. If you're seeing flight times of 10 years to go from, say, for the Centaurs to move from Jupiter to Neptune and maybe vice versa, what implications does that have for just the overall structure of the solar system itself? Is everything in places that it isn't expected to be a lot more quickly than we ever thought?
Yeah, that's actually a great question. So if you think about solar system dynamics right now, if you look at the current state of the planets and you look at how that gravitational interaction conditions sort of the structure of the solar system, the different belts we have, the main asteroid belt, the Kuiper belt. You can look at the signatures in those belts. Why are these guys certain inclinations? Why are they in this distribution they have? And that was really a lot of that understanding came from the idea that the early solar system, as it migrated out, as these gas giants migrated out, that actually causes instabilities in these orbits of these small bodies. So Pluto, for instance, is not in the ecliptic plane because of this exact mechanism, which our colleague Renu Malhotra had done a lot of work in that regard. But the thing is when you study solar system dynamics now, you think about timescales on the order of what, 10 to the millions. It's millions of years or giga years. So you have these timescales that are incredibly long, and so a lot of that would sort of, it's almost like you're washing away some of the dynamics that is sort of inherent in this that we have not really put a lot of focus on in the planetary science community. Until now. So there's been a couple piecemeal studies showing the cometary sort of circuitous routes that they follow from these manifolds, but nobody's really put that understanding for this broad sort of to answer that question that you posed. So
yeah, it
opens up some new doors for sure.
I mean, definitely, when anything's working over, if you've got timescales that things are happening over decades compared to the kinds of time that has been happening in the solar system, billions of years,
right?
Whatever resonances we're going to get figured out. I know, for example, like the number of near-Earth asteroids that we have near our planet is constantly being replenished by Jupiter kicking asteroids out of the asteroid belt and in our direction, and then some number of them hit the Earth, and there will always be fresh asteroids coming our way thanks to Jupiter interacting with the asteroid belt. And so are there these like slower processes and faster processes kind of working in concert?
Yeah, exactly. That's one of the fundamental questions, is how do we connect that traditional picture of sort of these resonant instabilities that you're talking about? So you can be at the Kirkwood gaps in between Mars and Jupiter, where you have that paucity of asteroids that got kicked out from these sort of instabilities. Those things typically happen over thousands of orbital periods. not the, tens of orbital periods or less that we're looking at. So there is some, resonant hopping between different zones. So if you look at some of, like, if you take Latherma, which is a, comet that we have a really long history of in terms of its ephemerides, and if you look at its trajectory, it goes from an exterior region to an interior region, or maybe it's opposite, but it bounces between those two resonances. And what links those two is these manifold trajectories. So if you do like some numerical studies, you'll just see it kind of hop, and it looks like it's sort of a kick, a disjump or a discontinuation. But that's only because you're not framing the problem the right way. So there's a lot of deep understanding that can come from studying these as a mathematical structure and linking those with the hierarchy of more realistic models to try to paint that picture.
Now, Dee, you had some graphics you're going to show us, right?
Yeah, we do.
I'll let Dee describe the video he made. He's
all right. So
here you go.
So it started from this very beautiful picture of this interplanetary highway.
So this is from the earlier stuff. This is the interplanetary network from Ross and Lowe and others.
Yeah, this is exactly what you described as like saving a lot of fuel. And this is a general picture of all the satellites, all the comet asteroids we have in the solar system. And the gray one you can see is actually children gray, which kind of give us the intuition to have our structure started.
Right. So I guess what he's saying is that the Trojan and Greek asteroids, those are the co-orbiters with Jupiter. And so we actually were, Nataša, when she had done this study initially, she was looking at sort of the stability of those regions. And those are sort of, very clearly dark regions right here at Jupiter's orbit. So you can have really, long-term in those regions. There's very short-term stability outside of Jupiter's orbit and interior. And these are traditionally known as the planetary clearing zones. And people have known about this for a long time because there's overlapping of all those resonant effects that you were talking about. But in fact, this is at a much shorter timescale. So there's rich structure that occurs.
Wow, that's really cool.
And this one shows like
we don't have to go through the whole videos, but
okay.
Maybe we'll flip through some. That's the sort of the motivation for the title is Arches of Chaos.
Yes.
But this is a cool video that he made throwing out some objects that you can see. It goes the time scale pretty fast, but it got ejected beyond Neptune in 40 years. But I don't know if that was a particularly fast one. But
yeah, that's a very fast one. And this one shows a bunch of different trajectories that could be kicked out by Jupiter in this manifold.
So this is very not traditional picture of how you think of how things orbit, right?
Yeah.
So it's pretty interesting when you get into the details of it, certainly.
Wow. 38, and so you've got over 100 years, 38
years.
But as we were saying, it can also like kind of Pac-Man here, it can also eat up some of these bodies. Really, it's the different totality of solutions is sort of you can get a lot of different effects. So we haven't focused on all of those. And of course, a lot of people in the media, they cared about the spacecraft implications and how we found hyperspaces. They're not quite hyperspaces. It's not Newtonian physics here. So
yeah. But it sounds like the mother of all three-body problems.
The three-body problem is interesting in and of itself because, there's really no, closed-form solutions to it. And it's been challenging people in my field, so in celestial mechanics or astrodynamics for, you can stop the video here, I guess. It's really been challenging, our understanding for a long time. And I always say, like, if you took Star Wars and you look at Tatooine, right? Like, there's no way they would have been as advanced as us because they had two suns. And there's no analytical solution. So there would be no Tycho Brahe who would have done the observations that would have allowed Kepler to deduce his laws because it would have been a non-trivial solution.
Right.
Whereas, it's so fortunate that we were,
a single sun. Right.
With a single sun, because the three-body problem is very hard. So if you think of the totality of solutions, you drop something close to, the region of the Lagrange points where the gravity of both bodies is sort of equal, you can get a whole plethora of different solutions, and it's hard. It's really hard to predict what's going to happen.
I mean, I know that we're finding that the amount of time it took the planets to form just seems to be getting smaller, lower and lower and lower. And then in fact, now we're seeing that maybe even some of the giant planets formed on a matter of like thousands of years, very, very small time frames. Do you think this would almost act like a funnel, like as things like Jupiter are starting to come together? I can imagine it's just like fire hosing material into different parts of the solar system to help them turn into their planets as well.
Yeah, I don't think anybody has ever looked at the problem of the early dynamical history and where, how did these manifolds, because of course they're not fixed in space, so they change with the motion of the
and they
planet.
change as the planet changes in size.
Yeah, exactly. So there's a whole interesting array of studies you can do in that regard, and that's certainly not our expertise by any means. So
well, you got your ideas for your next collaboration, your next paper. Awesome. Thanks, guys. So if people want to find out more about what you're working on and sort of follow this study, where should they go?
So I don't really have a social media presence myself.
Good. That's a what? Yeah, instead you're publishing science papers. That's the right way to go. That's the right balance in life.
I'm pretty active on LinkedIn, and I started to use Twitter a bit more now with sort of promoting some of this work.
It's a trap. Don't do it.
Yeah, I've sort of been against social media since about 5 years now. But I host a lot of events, also in public outreach. So we're having a Space Debris Day. I don't know if you can throw that up there for the guests. But this is going to be also a virtual event. It's going to be free, offered through the H.R. Macmillan Center in Vancouver, where you're at.
Yep.
And it's going to feature a panel of experts that talk about space debris. So we're going to talk about the manifolds that can take space debris back to the Earth and clean up space. So when you have that starlight,
it's really interesting.
The mega constellations, you think about those from a space debris point of view, and they're not such a nice solution.
Okay. So see if I understand this correctly. Then, I mean, the way we've thought about traditionally in getting rid of space debris is force it to crashed into the Earth's atmosphere, and if the stuff is too high up, has too high of an altitude, then it's not going to return to the Earth's atmosphere for thousands of years potentially. But maybe you could kick it into a different trajectory, follow one of these manifolds, and bring it back into the atmosphere shorter than.
So a lot of my research early on, and a lot of my colleagues as well before me, but we've done this sort of finding those manifolds to get rid of space debris in that way that the Kirkwood gaps gets rid of those, and the asteroid belt, has those gaps in it. Sort of finding the Kirkwood gaps of space so you can put something in there and get it back. But it turns out the timescales are very large. Like you got to wait 100 years. So they're like the slow backlanes again. But we took a lot of that knowledge from planetary science and adapted it to the space debris problem. And now I think he is trying to give some of that back in terms of this stuff.
It's interesting. I mean, it really does sound like there's a lot more going on in the movements and the interactions of the planets and the gravity than we ever thought. One last question. Do you think something like this is going on at a Milky Way level with stars and gas and things like that? That's your other paper? All right.
Maybe Scott Tremaine can answer that. Got to talk to a galactic dynamicist. I don't think I have his book out here right now, but so that's another interesting question for some follow-up studies. But I don't think.
I mean, you don't have the same kind of like immense gravity in any one neighborhood, but it's an interesting idea to sort of see if this, again, it's sort of like, is everything moving around a lot faster than we ever thought? Which I guess is sort of an interesting idea. So yeah, super fascinating. Well, thank you so much, guys, for joining us on the Weekly Space Hangout. Really appreciate it, and keep us posted when you figure out the hyperspace. Is that what people are? Yeah, when you figure out the way to be able to.
Analogy, but
yeah, that'd be great. Yeah.
All right. Well, thanks again.
All right. Thanks a lot.
Bye.
All right, let's move on with the news portion of the show. All right, Morgan, let's start with the test of the SLS.
Yeah, so we've been waiting for this test for a little while, and this is the first time they basically put together SLS and decided to fire it all. And so we've been building to this now for many years. So they've been transporting various components of the SLS main stage to Stennis Space Center in Mississippi. For a while now, they hooked everything up to a test bed, so basically bolt the rocket down so that it can't fly anywhere, and then fire the engines. And the goal of this particular static fire was to simulate basically the entire flight of the SLS from liftoff all the way until payload deployment, which was a period of time between 8 and 9 minutes in length. And so this would include not only firing the rocket for 8 or 9 minutes, but also gimbaling or turning the engines to mimic the kinds of maneuvers that SLS would have to go through to test basically all the components of the system under the most realistic scenario they could in order to sort of shake out any kinks. And just to remind everybody, the SLS is fundamentally based on the space shuttle. The engines on the space shuttle are the same engines that have been transferred effectively to SLS.
The RS-25s.
Yes, and they are beautiful, incredible engines.
Yeah, they're, I'm sorry, I just got to stop for a second here. The RS-25s are the Ferraris, or the Lamborghinis of rocket engines. They were able to take, they are one of the most efficient rockets ever made. And as in the era of the space shuttle, they were able to eke out even more power out of them. And now in the new era, they're going to by making them disposable, they're going to run them even harder.
Yeah, so they remain among the most efficient chemical rockets ever developed. They were also the OG reusable rocket. They've been used for decades and decades. And then they're also going to be using an evolution of the solid rocket booster that was used to help get the shuttle off the pad. So the bottom line here is most of the technology in SLS is building on decades of flight pedigree.
Yeah.
So the plan for the green run was to put it all together, fire it up, and prove that it still works.
Right.
And the goal was to fly that whole 8 or 9 minute mission on the test stand. And they wanted to complete at least half that. And if they completed at least half of that, so about 4.5 minutes, they would have collected basically all the data that they needed to validate all of the various components. So they put it on the stand, they fire it up, and almost immediately things start not going very well. And the machine gets automatically shut down just over a minute into the test. So far less than the 8 to 9 minutes it was supposed to fly, and only about a quarter of what they were hoping minimally to attain to kind of do all their validations. And so on the day this happened, it all looked pretty bad. The NASA feed called out some sort of major component failure. People watching it saw these like bright flashes coming from one of the engines, and it just all kind of seemed like it's kind of the next giant hurdle for SLS. But in a little bit of good news, as they've sort of unpacked what happened, it's gotten progressively less and less bad. Mm-hmm. So number one, the reason it was shut down early was because of these extra tight parameters that they had put. Sort of the tolerances that they were going to allow the engines to undergo were very tight to avoid doing any real damage.
Yeah. And
one of those engines exceeded that extra tight tolerance by the sort of tiniest of margins. But that was enough for the computer to trigger the shutdown. The so-called major component failure turned out to just be a faulty sensor on board one of the engines. And the flash that people saw, which they thought might mean that the engines were sort of burning through and getting in contact with each other, turned out to just be a sort of the normal variation of the firing for the engine. And so instead of being sort of months to a year, it's potentially just weeks before they can kind of replace that sensor, refurbish the pieces, refuel the spacecraft, and do the green run again.
Right. Okay, good.
And so that's basically as good as a failure could be.
Yeah. That's
what it was, but it was still a failure of a system that fundamentally is the same system that we've been using for decades.
Yeah, it is a space shuttle.
It's not a good look for SLS.
Right.
But in the spectrum of SLS problems, this is way over on the sort of minor side of the spectrum.
Yeah, and I wonder, no one has said that the plan for going to the moon has changed, and if it had been like a catastrophic issue that would take them years of redesign, then that would be a problem. But as you said, if it is just weeks for them to refurbish everything and do the test, then it doesn't cause too much damage to their timeline, which is inevitably going to slip anyway. I mean, we know.
Right. The hope was to launch the first SLS this year, like end of this year, I think. And it's probably going to slip, as all things do, into next year. But this doesn't appear at this time to be a big roadblock to continuing the testing program.
Yeah, yeah. Well, that's good news. I don't feel like people were pretty harsh on NASA, actually. You know, the space news community was pretty mean right after. It's possibly I got sucked into it a little too. You know, I called it embarrassing. Maybe.
Yeah, well, you know, so much of NASA's effort right now, human spaceflight and science spaceflight, is tied up in the future of SLS. And obviously, there have been so many stumbling blocks thus far that I think it's understandable that people are sort of on a short fuse for yet more problems. But this is why it's important to actually go to the data and investigate the problem. And thankfully, we found that maybe we all jumped the gun a little bit.
All right. Well, then we don't have to worry about this enormous project going more over budget yet.
It's definitely going to work now.
It's definitely going to work. No doubt. No. I mean, like I'm so torn. Like on the one hand, it's such an amazing, like it is the space shuttle done right. But we don't know whether we need the space shuttle done anyway. Right now that we're seeing things like Starship. I mean, you think about like how long has SLS been in development, especially if you connect it with the original Constellation program.
Yeah, you're talking, you know, decades if you go back to Constellation.
Yeah. Are we 12 years? Like when did Bush announce? Was it 2004 that we're going back there?
2004 or 2005. So
yeah, 15,
okay.
Yeah,
so 15 years dating back to Constellation.
Yeah. And Starship didn't even exist as even an idea more than 2 years ago. And so but
so I'll throw this out there. There's a point of view on NASA sort of in general and human spaceflight in particular that it's sort of basically a really fun, really shiny jobs program. And so and SLS bears that out, right? NASA was basically told that they had to find a way to transition the entire manufacturing capacity of the space shuttle, which is spread across every state in the country, to a new program. And so if the goal is basically to pay a bunch of people a good salary to do engineering and high quality manufacturing and all of these things, then from that perspective, SLS has been a success. If your goal is to actually fly things in space and explore and do that kind of things, then the SLS has obviously been an abject failure to this point.
Right.
But that is only part of the story when you look at it sort of from a programmatic perspective.
Right. And I mean, still, like, again, I always sort of game this out. Like you can now launch human beings on the Falcon 9 with the Crew Dragon. But you can't launch the kinds of gigantic payloads that you would want on a Falcon 9. You could launch them on a Falcon Heavy, but then you can't launch people on the Falcon Heavy yet, although theoretically you could make it possible. But to do things like the Europa Clipper or to launch components of the Deep Space Gateway, you need something even heavier than the Falcon Heavy. You need an even more powerful thing. And nobody has made this yet. And so when it made sense that was the decision at the time, let's build this enormous vehicle for launching stuff. And yet here we are with Starship potentially around the corner and you're not getting, and so now it's looking like, okay, maybe we shouldn't have put so much energy and time and expense and fat contracts to various contractors and political needs. Maybe we should have started to shift over to more of these commercial providers. But it's such a tricky thing because still Starship is vaporware.
Absolutely. Until they can actually put it on the launch pad and fly it, it hasn't worked.
With people on board safely and bring them back to Earth, all of that. I mean, there's well, you know, in traditional way, there's 10 years of development to go. In the, I guess, Musk thinks he still says he's sending humans to Mars by 2026, no matter what. So, well, thanks for the update. I'm relieved, and I'm excited to watch the 8-minute hot fire test.
They're going to get it.
All right. Alan, what do you got for us?
Digital codes for stars, or at least digital color codes and how to represent them accurately, which should be a simple thing, right? I mean, as astronomers, we know a lot about color. We're always talking about the colors of stars, the spectral codes. You look at the Hertzsprung-Russell diagram, everything's colorful. But this is scientific data, right? It's a very, very detailed spectrum, and it doesn't really match how the human eye perceives color. Right, we're trying to filter everything through just red, green, and blue, whereas a spectroscope gives you all the colors, right? Every single frequency. So there's a paper that came out just a few weeks ago. From, I hope I pronounce the names correctly, Jan Vincent Haar and Renee Heller, trying to map these colors into something that we can use, say, like a hex or RGB codes that you can use in Photoshop, but an illustrator can use to draw an accurate representation of what a star's color actually looks like. And they started by just modeling what the colors would be from the black body outputs of various temperature objects. And was their starting point. And I think that's maybe where a lot of you're sort of based on the way we've always done these things comes from. It's where the names for the different stars comes from. We have red dwarfs and blue giants and so on.
Yeah, the color it's right there in the name.
Right, and is it accurate though? And it turns out that the next thing you got to do is you start modeling what the color will look like once you take into account your absorption spectra, right?
Like the atmosphere of the Earth.
Of the star itself.
Right. Okay. But I'm sort of imagining, like, as you said, you've got the black body radiation of the star, just like literally just the average color of the photons that are streaming off the star. But then you've got, as you say, the absorption spectra of the star itself. So you've got various chemicals in the star starting to pull away some of the photons. You got intervening gas and dust that's in between us. And then you've got our own atmosphere that is potentially changing the length, the color of the star. And also depending on whether it's like at zenith or whether it's down near the horizon. So
these are all factors. Yeah. I think that they're looking mainly at the color in space. So our atmosphere is not a factor. But if you look at the spectrum of any star, it's not that lovely smooth black body curve. It's a spiky notchy thing. There's a lot of wavelengths are quite heavily filtered out. So once you take that into account, the color the perceived color starts changing. Then they start taking into account the limb darkening effects. While the center of the stellar disk that's facing you is quite clear. You can see this quite clearly in solar photography, right? It's how the edge of the sun is quite a bit dimmer and darker.
Yeah,
and that then affects the color perception as well. There's color filtering effects there as well, but that got a bit complicated. I think they didn't take that into account in the modeling. And anyway, the end result of all of this is they now have a nice table for each different spectral classification of stars showing what they actually look like. And I don't know if you've got the
I've got the paper, but I can't share it right now.
Pity. If you scroll down about to the middle of the paper, they have your standard color wheel with each of the different spectral types mapped on it.
Yeah.
And it shows a couple of things that I think would be surprising to. I think if you study this in detail, I think we all knew this, but it's not how we think about it. Brown dwarfs are not brown. Red dwarfs are not red.
Yeah.
They're more of an orange. Yellow dwarfs, like the sun, are very, very close to white. Whereas the blue giants turn out to be extremely blue.
And nothing gets anywhere near the green end of the spectrum, and very little makes it into yellow.
Stars.
Yeah. Yeah.
In the body of the text, they point out that even yellow, you don't get yellow stars. We think of the sun as yellow, but it's not really.
Yeah, it's white.
Yeah, it's white.
Yeah, yeah.
Yeah.
It's
So
kind of interesting.
this is useful. Sorry, carry on.
Oh, no, I was just going to say, yeah. I mean, this is sort of this funny conversation that I get in with people. It's just that, yeah, that if you were in space and you were looking at the sun, which you shouldn't, without some kind of filter,
what does it actually look like?
It would actually look white. It looks very white.
Yeah.
And we're seeing it yellow. And even in the middle of the day, if the sun is directly overhead, the sun actually looks very white. It's only when it's just that the times when we can see the sun, when it feels like we can notice it, is when it's close down to the horizon. It's just about to set, and that's when it takes on that yellower hue. And if there's a significant amount of dust in the atmosphere, then it turns even more reddish. And it's purely the atmosphere that's making the sun look the way that it does.
Yeah. I think it matters because if you've ever shown off imagery or shown people your own photographs, and once they understand a little bit about where those images come from, that there's always a bit of processing involved, or the cameras might be showing you non-visible wavelengths, they always want to know, but what does it really look like?
Yeah, yeah.
Right? They always ask that.
Yeah.
And now at least we have some idea, the actual colors. And when we start doing illustrations in popular science articles or in textbooks, at least we can give something that's a bit more. I wonder honest, if you haven't been lying, but
yeah. So I wonder. I mean, could you say if you've got one of those Philips Hue bulbs, could you set it to the colors of the different stars to run through the gamut?
Those things will take RGB values, right? Same as if you're designing a website.
I'm assuming so. Yeah, that you could set RGB values and sort of see what the different colors would look like. Be kind of fun to have a light going that just cycles through all of the RGB
I'm
values.
in a Beetlejuice mood today.
Yeah, exactly. Yeah, totally. That's awesome. Thanks, Alan.
Yeah, definitely.
All right, Morgan, bad news.
Let me hit you with another one. Not a great week for NASA, all things considered. So we've been talking and following NASA's InSight mission ever since it was under construction many years ago. You might remember originally it actually got delayed by 2 years. Then finally it got to Mars and it landed and it started trying to deploy its experiments, and it ran into another problem. There's really sort of two big experiments on InSight. And one of them, maybe the most interesting one, was trying to drill down into the Martian surface to quantify the rate at which Mars is losing heat. So we all have this picture of Mars billions of years ago as being kind of this warm, wet planet. There's a lot of evidence of water on the surface. It probably had a relatively thick atmosphere. It could have been actually quite Earth-like in many respects. And then today, Mars is cold and dry and dead with a very thin atmosphere. And so over that period of time, it has lost a lot of heat. But we don't really have a good handle on how much or how quickly that heat is being lost. And so one of the goals of InSight was to drill down about 3 meters and to drop a thermometer. And 3 meters down is enough insulation above you that the sort of daily diurnal cycle of the weather doesn't affect the temperature that you're going to read. And so the goal was basically to take Mars's temperature and use that to estimate the rate of heat loss today. And then you basically run time backwards to figure out when Mars must have had enough internal heat to, for example, sustain an internal magnetic field that would protect the atmosphere, and that kind of gives you all the things you need to have that nice, warm, wet surface. The problem is you can't fit a 3-meter drill bit on a 1-meter spacecraft. And so they had come up with this kind of clever digging solution that they called the mole. And it's often been described as like a self-hammering nail. And the idea was this thing would basically go into the ground and then just kind of hurl itself forward to work its way into the ground. And the whole idea was predicated on the fact that everywhere else that we've tested Martian soil, it's been relatively dense. And so you can actually dig into it. But it turns out that wasn't the case where InSight landed. And so they tried to start hammering in, and it's just like nothing happened. It would go in like a few centimeters, and then it just kind of pounding away and going nowhere. It's kind of like imagining trying to like take a hammer and pound a 2x4 into the beach. You know, you're going to get it a few inches in, but eventually the soil is just kind of so waterlogged and soft that it just bounces back at you every time you hit it. And that's exactly what the mole was encountering. And so they've tried all kinds of ways to sort of help the mole along. But this week they finally just gave up.
Yeah.
And they said, you know, sort of too bad. And this is, you know, this is an unusually large failure for a NASA mission. Of all the space agencies, NASA is by far the most conservative. And I mean that in the sense that they're only basically going to fly things that are like almost certain to work.
Yeah.
And in part,
failure
that's
is not
why,
an option.
Yeah, failure is not an option in the bad way, you might say. But it's also why we can spend billions of dollars on these missions and not have the kind of costly failures that undermine NASA's credibility with the taxpayer and with the government.
Yeah.
And so, you know, this being sort of 1/3 to 1/2 of what InSight was supposed to do, and for it not to be working is a big thing. But it's also just the risk you're going to take with going somewhere new and trying something different. You know, we couldn't know what the surface of Mars was going to be like where InSight landed. And in its failure, we've learned something about the dynamics of the Martian regolith at this location. But we're not going to learn about Mars's temperature or the heat flow out of Mars. And that's just too bad.
And it is still a very interesting question, because if you ask a planetary geologist who specializes in Mars, like, when did Olympus Mons erupt last? Their answer is like sometime between several billion years ago and 5 million years ago. Like, they just don't know how long it has been since there's been active volcanism on the surface of Mars. Clearly there was a lot. You know, the tallest volcanoes in the solar system are there on Mars, but we don't know when they actually shut down. They might still be active, and they might erupt in another few million years. We just don't know. And this was the tool that was going to answer this question, that was going to tell us. It's funny. So this is the mole was run by the German space agency, and they're the same people that delivered all kinds of really clever, creative solutions with the Hayabusa mission. And I really enjoy. You know, I've gushed about how much I really like the JAXA and sort of the cool, creative willingness to fail. It's the opposite. Like, failure is expected.
JAXA is on the YOLO end of the spectrum.
Total YOLO. That's exactly it. Yeah, YOLO.
And NASA is as far from that as you can get, and then ESA and everybody else is somewhere in between.
And I do think that the German aerospace is in that YOLO spectrum as well. They've supplied a really clever lander for the JAXA mission. They're the ones who worked on this mole, and they're not all going to work. So I think this is to be expected, and I appreciate them attempting to get an answer to this question. And they tried so hard.
InSight was different in the sense that, it was incredibly international. Like you mentioned, the mole came from Germany. The other major instrument, the seismograph, came from the Italian Space Agency. But the part that NASA contributed, which was basically the spacecraft, was sort of pieced together from the leftovers of other missions. So the spacecraft body and everything, it came from the Phoenix Mars lander from 2007. And some of the cameras and things came from the old Mars rovers, the backups for Spirit and Opportunity. So in a way, this was kind of an opportunity to go outside your comfort zone a little bit, because you weren't investing very much in the rest of it. You were kind of using off-the-shelf stuff that was otherwise just going to sit around. And they rolled the die, and they didn't get what they wanted. But that doesn't mean they shouldn't have tried.
Do you think that there's any science that could still be done with the mole? Like you're saying, like, the goal was put it under, try to keep it away from the temperature variations to the point that you could start to detect the temperature of the surface of the planet. Could you use some kind of big data to still tease, even if the mole is only, because it's covered. I mean, it's at least whatever say it is the length of the mole in the ground. Could it tease out some kind of temperature data with some kind of clever solution?
I mean, when you're talking about another planet, basically, literally anything you can learn is new and interesting. And so, like, the fact that I bet you there have been dozens of papers that have been written or will be written about the qualities of the soil based on the fact that it didn't work. Every different technique they tried was generating interesting data. I don't know exactly how the thermometer worked, like whether it would work in its present location or not. But if it could, I bet they've taken some data to try to work that out. You know, the other major instrument's a seismometer, and I bet all of this banging and clanking they've been doing with the mole has been picked up by the seismometer. And that's telling you something interesting about the way in which the regolith is conducting vibrations. And so I think they are probably mining all of this flailing about for novel data that they otherwise wouldn't have collected.
Yeah.
And hopefully can turn that into some unforeseen insight, no pun intended, that they otherwise wouldn't have been able to get.
Arjone says, we need to figure out this mole thing before we try anything on Europa. I want my space shrimp. So, yeah, I mean, it'll be a different technology melting down through the ice on Europa, but still, it's going to require some novel solutions for sure. All right. Well, thanks, Morgan. Well, we've run out of time. We had one more story, but I think we've run out of time for today. So unfortunately, we won't get to it. But the short version is there's 3 interesting CubeSats with 3 dramatically different advanced propulsion systems, which are going to space. One is going to be launching with a fancy Hall effect thruster, an ion engine. One that's going to be using a tether system to lift up using electricity and no actual propellant. And then the other one that NASA just announced today is they're going to test out water. They're going to take water, they're going to separate it into hydrogen and oxygen, and then use that as a propellant, and obviously as a precursor to trying to mine water from comets. Pretty cool ideas.
Well, CubeSats are the antidote to the InSight situation, basically, because they are like the cheapest conceivable way to test out this whole range of new ideas.
Totally.
And even when InSight was being put together, over the last 15 years, CubeSats weren't a thing. In the sense that you could, one of these 3 stories was like a bunch of college kids in a lab building a CubeSat. The fact that you can launch like that is going, and it has already enabled the development and the test of all kinds of new techniques. And all of those are lowering the risk for your traditional major space missions, whether they're from NASA or ESA or JAXA or what have you, and testing out whole new ideas. And so I think we're just right at the beginning now of the sort of world that's going to be unlocked by the combination of these cheap launches to space and these cheap satellites to construct. And the kinds of things we're going to get to do in the next quarter century are going to be so much cooler than they otherwise could have been, because CubeSats are going to prove that it works to the powers that be.
There's a real value in just pure exploration without necessarily some kind of big goal, like just investigate ideas, see what you can do, follow your curiosity, and then roll that technology into something bigger. There's been a ton of really great technologies that have been developed. They were developed, in some cases, they were imagined back in like the 50s and 60s that never made it, have never flown, just because nobody ever had the guts to actually attach it on their precious
like that tether
spacecraft.
CubeSat. Everybody should look that story up. That idea is just like bonkers.
Yeah.
And there's no way that you could have convinced somebody to pay $100 million to try that out, because it's just like silly time.
Yeah.
But if they can make it work, then suddenly you have a solution.
Yeah.
And to this huge set of problems that satellites face.
Yeah. Yeah. There was one test of this technology on the space shuttle back, I think, in the 90s. They tested a tether as a means of gaining altitude for the space shuttle, and theoretically it did work. So just by running electricity down a wire you cause your spacecraft to raise its altitude, which is such a great idea.
Magnets.
Yeah, magnets. Yeah, exactly. All right,
It's all magnets.
Morgan, you're on my screen. Where can people find out more? Tell us what you're working on.
Yeah, well, I'm working on some cool videos for SciShow, as always. I just wrote one about the Great Leviathan at Parsonstown, the sort of last of the great pre-modern telescopes. It was basically had to have a castle built around it, so that's pretty awesome.
Yeah.
And you can always find out what I'm working on over at morganrenberg.com.
Right on. Alan.
Yeah, well, you can always listen to the Urban Astronomer podcast at urban-astronomer.com, or just follow me on Twitter, UAstronomer, see what I'm doing.
Excellent. All right.
Yeah.
And I've got a interview on Friday I forget the guy's name. I have to post the event, but I'm going to be interviewing someone about building an ice robot that forms its shape out of ice that it finds on a comet. So they've tested out technology. It can heal itself. It's a pretty clever idea. So we'll be talking about that on Friday. All right, I can put everybody back on the screen who's still here. There we all are. Thank you, everybody, for joining us this week on the Weekly Space Hangout. Thanks to my co-hosts, our special guests. Thanks to our moderators and everyone in the community. I'm watching the chat. Thanks. I know Beth has been looking at the chat over on the Twitch side as well. So thank you, everybody, for watching us today. And we will see all of you next week. Thanks, everybody.
See you all.